Last talk of the session, we have Alper Çakan, who's going to talk about unbounded leakage resilience and intrusion detection in a quantum world. Alper, please take it away.
Okay, thanks for the intro. This is joint work with Vipul Goyal, Chandra Liuzeng, and Joe Ribeiro. So I'm going to be mainly talking about the age-old problem of storing secrets. So as you all know, in most of crypto, by default, we assume that the adversary attacks are schemed through some well-defined channel. For example, in case of encryption schemes, the adversary sees some ciphertexts, and in case of public key encryption, sees the public encryption key, and later it tries to decrypt some challenge ciphertext. In case of signatures, it sees some signatures, and later it tries to forge a new signature, and so on. And crucially, we usually assume that the adversary has no information at all about the secret keys of our scheme. Unfortunately, real-life attacks do not conform to this ideal assumption, and there's a whole range of attacks called side-channel attacks that violate this assumption. For example, through side-channel attacks, the adversary can learn some partial information about our secret keys through various methods. For example, there could be there's various attacks in the literature like timing attacks, power analysis attacks, electromagnetic radiation analysis attacks, and so on, where the adversary measures some quantity about our system and they learn some partial information about our secret keys. And these attacks have been catastrophic for various cryptographic schemes, and the important question here is how to keep our secret keys secure in face of such attacks. So, as probably most of you already know, there's a whole line of research about this in the classical literature called leakage resilient crypto, where people have designed various primitives, and they showed that their constructions can resist various side-channel attacks in some sense. And one of the important points in this area of research is modeling the side-channel attacks, which can be in very different forms as we just saw here. And one of the most commonly studied models is the so-called bounded leakage model, where the adversary specifies some function and it learns the output of this function on the secret key as its leakage. And we will require that the usual security requirement, like the semantic security in case of PK or unforgeability in case of signatures and so on, should still apply even when adversary learns this leakage on the secret key. And crucially, in the bounded leakage model, the most commonly studied model, we assume that the leakage function specified by the adversary has a bounded output length that's smaller than the length of the secret key itself. And why do we assume this? One of the main reasons is that otherwise we cannot have security. Because otherwise the adversary can just choose the identity function and can learn the whole secret key, and there's nothing we can do. Okay, so in this work we show that quantum information is actually fundamentally better for this task of storing secrets. And this gives us a brand new application of the quantum no-cloning theorem. More precisely, we design various schemes in the plain model for various important primitives such as public key encryption, signatures, PRFs, and so on, where the secret keys are stored as quantum states and they can tolerate arbitrary unbounded leakage, and there are no unjustified bounds on the leakage size. And everything other than the keys will still be classical, like the ciphertexts or the signatures and the public keys, they will all be classical, only the secret key will be a quantum state. Okay, so let me formally define our model first. I will be talking about PK case mainly for simplicity, and the other cases are similar. We will be encoding our secret key as a quantum state, and our first requirement is correctness. For honest ciphertexts, we can decrypt them with overwhelming probability using our quantum secret key. And this is an implication through the gentle measurement lemma that says that we can do this without damaging our quantum secret key at all, which means that we can repeatedly use our quantum secret key for decrypting various ciphertexts n number of times. And moving on to our security experiment, we will call this local operations and classical communications leakage resilience security, or LOCCLR for short. In the security experiment, the challenger samples the keys of the PKE scheme, and the public key is sent to the adversary, and the adversary adaptively, depending on the public key, specifies some leakage circuit, which will be a quantum circuit with classical output. And this circuit will be applied to the quantum secret key, and the measurement result, which is the leakage, will be sent to the adversary. And the adversary will keep specifying adaptively leakage circuits for any number of rounds as long as it wants. And each round, the leakage circuit is applied to the post-measurement state from the previous round. And after the adversary yields leakage phase, it will receive a challenge ciphertext encryption of M0 or M1. And we will record that it cannot guess which case it is with probability better than random guessing, which is 1/2 plus negligible. So even with all this information about the secret key, it cannot do much better than random guessing. And as I said, the notion will be similar for other primitives like signatures and PRFs and so on. There will be a LOCC leakage phase where the adversary will obtain a LOCC leakage on the secret key. And afterwards, with the state that it has accumulated so far, the adversary will participate in the usual security game of that primitive. And to reemphasize, the leakage functions here are arbitrary. There are no bounds on the size of them. And in particular, the leakage can be much longer than the size of the key itself, which is obviously impossible to achieve in the classical setting. Okay, so one question here is classical leakage justified? And we believe it is because, as we just talked about, leakage is obtained through some side channel attack, and the adversary will have no direct access to our system. And this is most naturally modeled as observations and measurements, which are all classical information. And this actually readily captures all the existing attacks, side channel attacks we just talked about. A related question is, what if the adversary directly breaks into our system rather than trying to obtain some partial information through side channel attacks? And obviously, it's impossible to achieve anything in this setting, even in the quantum world, because the adversary can simply take the quantum secret key. However, we show that in the quantum world, we can at least detect such attacks, which is impossible in a classical setting because you can copy classical information without any disturbance, without being detected at all. And we introduced the notion of intrusion detection and security, and we show various schemes like FE signature and differing sophistication and so on that satisfy this intrusion detection security using quantum secret keys. Okay, before moving on to our constructions, let me talk briefly about a related notion called copy protection security, which has been studied a lot recently. So in copy protection, the secret key of the PKE scheme is encoded as a quantum state, and the adversary receives a single copy and tries to create two functional copies of this state. Or more formally, it will create two so-called pirate adversaries that are possibly entangled, and these adversaries will receive their own challenge ciphertexts, encryption of M0 or M1, and they need to be able to simultaneously correctly predict which case they are in. And we require that they cannot do so simultaneously with probability better than 1/2 plus negligible. So crucially, the baseline success probability here is 1/2 because the adversary can give the key to one of the pirates and the other one can just guess randomly. So why do we care about this? Because actually there is a natural reduction idea from leakage resilience to copy protection as follows. So we know that the classical info is easily copyable. And if leakage allows for decryption in the leakage resilience games, then we can possibly simulate leakage and then copy this leakage to get an adversary for the copy protection game. And this would possibly give us a reduction from the leakage resilience to the copy protection setting. And there's already a long line of work on copy protection, so we can possibly get LOCC leakage resilience for free from the existing schemes. So there are a couple of challenges here. First of all, the LOCC leakage adversary obtains some leakage over multiple rounds, and its final state will be a quantum state that possibly depends on all the leakage circuit choices it's made so far over the multiple rounds. And the state, as I said, is a quantum state, so we cannot necessarily clone it to get two pirates for the copy protection experiment. Another problem is that in the leakage resilience game, we had a single adversary, whereas in the copy protection game, we have two adversaries. So in this reduction, if one LR adversary succeeds with probability 1/2 plus 1/poly, through this reduction, we will get two pirates that will independently succeed with probability 1/2 plus 1/poly, and the probability of them simultaneously succeeding will be the probability squared, which is going to be close to 1/4, which is much smaller than even the trivial baseline attack. So even if we could somehow clone the state of the adversary, this still wouldn't work. Obviously, this is not the only possible reduction from copy protection to leakage resilience. And the question is, can there be smarter reductions to get leakage resilience for free from the existing constructions? We actually show that the answer is no. we show that relative to a unitary quantum oracle, there exists a scheme that satisfies copy protection, but it doesn't satisfy LOCC leakage resilience. In fact, the scheme we construct does not even satisfy one-round adaptive leakage resilience, while it satisfies copy protection security. So we will have to do work to get this new notion of LOCC leakage resilience. Okay, moving on to our construction. Our construction will be based on coset states, which are equal weight superpositions over elements of some subspace coset of F2 to the lambda, with some phase that depends on the elements in the superposition also. And we will also be using the so-called membership checking programs for the so-called primal and the dual cosets. And these coset states satisfy a very nice property called monogamy of entanglement, which is formalized as follows. The adversary receives a random coset state alongside the obfuscations of the membership checking programs for the primal and dual cosets. And it tries to create two pirate adversaries that will later try to output vectors in the primal and the dual coset, like here. And after the splitting, they even get the subspace description, but of course they don't get the coset shift elements S and S prime. And previous work showed that no polytime adversary can win this game with probability non-negligible. Okay, so one of our technical contributions is we show a new LOCC leakage resilience property for coset states. So similar to the LOCC LR game for PKE, we will have some adversary that first receives the obfuscated membership checking programs for a tuple of coset states, and later it receives LOCC leakage adaptively over multiple rounds on this tuple of coset states. And after it is completed with the leakage phase, it will receive a random challenge string, and it will try to output vectors that are either in the primal coset or in the dual coset, depending on the bits of the challenge string. And we show that no QPT adversary no polytime adversary can win this with probability better than negligible. So let me talk briefly about how we prove this property. So as we just saw, monogamy of entanglement game has kind of a copy protection flavor where the adversary is trying to split some kind of quantum state, whereas the property we're trying to show here is a leakage resilience property. And as we talked before, there are a couple of problems like the unclonability of the final state of the leakage resilience adversary and the one adversary versus the two adversary problems and so on. So how do we get this LOCC leakage resilience property for coset states? So our solution proceeds in two steps. We first move on to the information theoretic setting using a technique called subspace hiding obfuscation to remove the membership programs. And the other issues we solve by showing that we can actually force a collision in leakage circuit choices of the adversaries by repeatedly running multiple simulations of the adversary. And once we get the same leakage circuit choice at a particular round, we can leak once and reply to multiple copies of the leakage adversary simulation. And we show that exponential time is sufficient to start with many copies of the initial state of the adversary and end up with 2 copies which you can use as the pirates in the monogamy of entanglement game. And exponential time is fine in the information theoretic setting. Okay, finally, our full construction will be, the secret key will be the tuple of coset states, just like in the leakage resilience game. And public key will be the obfuscated membership checking programs for the coset states. And to encrypt the message, we sample a random challenge R, and we obfuscate this program that verifies the input vectors according to the random challenge hard-coded R. The program checks if the vectors are in the correct cosets, primal or dual, depending on the bits of R, just like in the challenge phase of the leakage resilience game. Okay. So this is actually the same as the copy-protected PKE construction of CLLZ21. But as we just said, there cannot be a black box reduction from leakage resilience to copy protection. So we need to actually show a new proof, and we crucially need the LOCC-LR property for the coset states that we proved. Okay, maybe I can skip this. And the other notion we introduced was the intrusion detection security. As we said, the adversary might, in some cases, can completely break into our system rather than obtaining side channel information, and it can obtain quantum information, and it can also cover its tracks by modifying the leftover state. And of course, we cannot have resilience security in this case because the adversary can just take our key, but we show that we can have detection security. In the detection security game, the adversary applies some arbitrary quantum circuit to the key, and the challenger then runs some test intrusion procedure, and if the intrusion is detected, adversary loses. If it's not detected, adversary will not be able to gain any advantage over random guessing. And we prove that this is equivalent to the certified deletion with public testing established in the quantum literature. Finally, here's a recap of our results. We construct various schemes with LOCC leakage resilience based on IO and LWE. We also have some intrusion theoretic constructions for secret sharing, and we also have various intrusion detection results. And that's it.
Thank you. We have time for one lightning question.
So maybe for simplification, but you presented your kind of result for public encryptions and similar schemes work, but is there some kind of, I don't know, some abstract property of take classical information and code it quantumly, and if it satisfies some properties, it will generically give you leakage resilient for any classical primitive, like public encryption and so on, or is this impossible?
So you're saying that we just take some like classical scheme and encode it quantumly in some form, like a general compiler?
Well, did you define some kind of, a primitive, take classical information, outputs quantum state, define some property of that quantum primitive, like, I don't know, leakage resilience one, and then show general compositions that take any classically secure scheme, signature encryption, apply that primitive from classical secret key to quantum state, and it's automatically leakage resilient. I mean, that would be like the best result if it's possible.
Right, yeah, that's correct. So in some sense, most of our constructions here, like PK, PRF signatures, they follow similar templates, like the secret key is the same type of state, it's the coset state, and there's some kind of obfuscated program that verifies that coset state to be able to execute the functionality like decryption or evaluation. But currently we don't have any general compiler composition like you mentioned, but that would be a really good result. I don't think it's impossible, but I don't have any ideas how to do that.